Hi guys, so I'm going to be taking you through a summary of our concept paper, which is titled Contrastive Knowledge Distillation for Banana Leaf Disease Diagnosis using Sparse Capsule Networks. So I'll start with the abstract. So basically, our concept paper proposes the development of an AI-driven system that leverages a multi-model to automatically detect banana Xanthomonas wilt, opponent bacterial wilt from banana leaf images, and then provide text-based advice based on those predictions. So our system consists of a multi-model, which uses approaches like knowledge distillation, sparse learning, contrastive learning, as we are going to look at later, for higher efficiency and better disease feature learning, which will cater to some of the computational problems we've also listed in the paper. So some of the keywords used in this paper to give us an understanding of what the system does. We have knowledge distillation, contrastive learning, sparse capsule networks, computer vision, deep learning, overfitting, neural networks, and so on. So the background for our project, we know bananas are vital crops for most people in Africa, but most times people face a problem of not being able to detect these diseases in time, and this would lead to substantial crop losses. So this project will combine two key components. We'll be using a computer vision model that uses capsule networks for image classification to detect signs of bacterial wilt from the images. And then we'll also be using a natural language model, which will provide customized advice to those farmers based on the detection results. So some of the technical definitions here, we have contrastive learning, which is a self-supervised learning technique, which involves training a model to differentiate between similar and dissimilar objects. It's like teaching a machine to distinguish between objects. Then we have knowledge distillation, which is a form of model compression that allows a relatively simple model to perform tasks almost as accurately as a very complex model. So a pre-trained model transfers its knowledge to a student model, and the student model learns from this teacher model. Then we have sparse learning, which is a technique where models learn only from the most relevant features. It maintains sparsity, so it's able to reduce computational power and also improve efficiency by eliminating redundant parameters and all. Then we have sparse capsule networks, which are an advanced type of neural networks, which are used in image classification. So we'll be using these by incorporating sparsity into the structure of the capsules so that they detect what we want them to detect. So our problem statement, the domain-specific problem is that bacteria will spread rapidly in banana plantations, but farmers are not able to know this because they don't know, they're not able to tell the signs and symptoms early enough. So this could lead to significant losses for farmers. The traditional approaches that have been used for disease surveillance, like monitoring, field work visits, are very tedious. So this approach lacks the ability to provide precise data on these bacterial wilt infections. So it hinders effective disease management where bananas are grown. Then the computational problem, since we are going to be using an advanced convolutional neural network model. The problem with these models is that sometimes they tend to overfit, and they also require large training data. And then sometimes they fail to learn the special relationships between features in an image. Like, for instance, this time we're talking about like leaf textures, leaf structures, and everything. So there's also a challenge for misclassification when it comes to image augmentation, when we are trying to avoid overfitting. Then these models also require substantial memory and processing power, but this can lead to increased training times, and then it will also lead to increased run times, and that's not really practical for us. So our proposed solution. First, we have two models. Remember, we are doing a multi-model. So our computer vision model, we use a sparse capsule network. So the advantage with the sparse capsule networks is they are able to understand special relationships between leaf textures and symptoms. So this will allow us to determine the level of the bacterial infection in a plant, in a leaf, whether it's at an early stage or a moderate stage or an advanced stage. So with this sparse capsule network, even if you're using a limited amount of image data, it doesn't matter because it reduces overfitting, which maintains the computational efficiency of the model and also reduce training time. Then our natural language model will use models like GPT, which are going to be used on agriculture data sets that will give us the information we need on prevention and treatment strategies for these banana leaf diseases. So the model generates detailed advisory text based on the detected condition of the plant, and then provide prevention or treatment strategies if the plant is infected. So the special hierarchies that we got from the capsule network can also be mapped to the natural language model to increase efficiency. So how the proposed system will work, our system will be accessible via a web interface, so that when someone uploads an image of a banana plant, the image is pre-processed, and then the trained capsule network will classify the image and assign it a severity level, whether it's early or moderate or severe. Then the detection results will be passed to the natural language model as input. And then based on predetermined knowledge and the training data we are going to put into that model, it will give us customized advice based on the results that it brings. So for our data set, we are going to be using the banana leaf disease images data set. We're going to be using it for our capsule network model, and it contains about 1,200 images of banana leaves under 3 categories. There's the category of the healthy banana leaves and the leaves that are infected with bacterial wilt, and then the ones that are infected with Sigatoka wilt. So each of these images has an approximate size of about 6 kbs. Image preprocessing and filtering will be performed on the collected images to enhance image quality necessary for further steps like augmentation, feature engineering, and all those. So we shall also be performing feature extraction to recover high-level features of these leaf infections in the image, so that we use them for training and testing our capsule network model, and also to be used to evaluate the model, its performance based on the accuracy, the precision, and the F1 score. So we also have references listed. The resources that we used during the making of this concept paper. Yeah, thank you.